Hi everybody, welcome back to Chem 121. It is Thursday evening of week 7, which means we are almost done with the quarter, believe it or not. There is some stuff due today, so quiz number 6 is due tonight. Make sure you get that in by the deadline. I will be closing the quiz tomorrow and then posting all the answers once everybody has gotten it in. Lab worksheet number 4, which we went over yesterday, is due next week. It is not due today, so just be mindful of that. And of course, if you have any questions about those, you can direct them to me, send me an email, and I'm happy to answer them. We're going to finish Chapter 7 today. There's really not that much left of Chapter 7 to talk about, so this probably won't take more than an hour to finish. And then we'll move on to Chapter 8 for a little bit. So yeah. What we're going to talk about today is how phases change between one and another, and we're going to assign some terms to that. How the energy from the surroundings will move either into them or out of them. And then we'll define some stuff so that we can assign what is happening to words that you are familiar with, like evaporation and boiling. So that's the whole premise of this section. So the first thing we want to do is we want to focus on the diagram at the bottom. This diagram down here indicates the different ways that phases can change state. For example, if I have something that's a solid and I melt it, it becomes a liquid. Likewise, if I allow my liquid to evaporate, it will become a gas. You'll notice that I'm using the word evaporation here and not boiling. There's a reason for that, and we'll talk about that in just a little bit. Now, there is a way to turn solids directly into gas. This is called sublimation. You've probably not seen sublimation before, unless you did laundry and tried to dry something out when it was below 0. Then any water that's in your laundry actually freezes, and then the ice itself evaporates. You can actually see sublimation occurring if you put ice cubes in a tray in your freezer and then leave it in the freezer for a very long time. The ice cubes will slowly disappear because the top layer is evaporating. Or is subliming, I should say, to use the correct terminology. Now, all of these terms on the outside, and I've underlined them all in red. Let me get sublimation here. All of these require energy to do. If I want something to melt, I have to put energy into it. If I want something to evaporate, I have to put energy into it. If I want something to sublime, I have to put energy into it too. The other terms that are all on the inside, I'm going to underline them in blue. Require that energy be lost for those processes to happen. In other words, if I want to freeze something, I put water in the freezer, I have to take the ambient energy out of the water in order for it to do that. That's what a freezer and a refrigerator do. They take the heat out of things and then pump it out the back through the compressor. If I want to turn something that is gaseous into a liquid, I have to cool it down. For instance, if you have taken a shower and the water is set to a very high temperature, the room that you're in gets very, very steamy. When the steam strikes a cold surface, such as like a wall or the mirror, the water then condenses. It becomes liquid again, and you get drops on the mirror, and then they run down the mirror, and you have streaks, and you have to clean it. But the reason that they condense into water droplets is because the mirror is colder relative to the water vapor that's in the air, and when the water vapor loses that energy, it becomes liquid again. Deposition is not something that we'll probably ever run into or talk about in this class, but it is just the opposite of sublimation. So each of these things is a change of state. The ones on the outside require energy, and the ones on the inside require the loss of energy. We're going to call those energy changes, and we're going to assign terms to these on the next page. So if something needs to lose energy, the term for that is exothermic. The energy goes out. And if something requires energy, we're going to call that endothermic, which means the energy goes in, because endo is in, exo is out. And so that should be just what this page is going to tell you, and you already saw all the answers to that question right here, so we're just going to keep going. Now, we're going to talk specifically about evaporation in more detail, because evaporation is interesting. So, specifically, molecules can escape from the liquid phase, and then they turn into what's called a vapor. Now, the definition of a vapor might be a little bit different from what the definition of a gas is. And so we're going to go over here. Oh, that lined up really nicely, actually. We're going to draw a picture of a container that contains a liquid. So this is my liquid. And in my liquid are little molecules of the liquid. And they should all be the same size, but I can't draw. Now, these molecules in the liquid can move any which way they want to. Some of those directions that they may choose to do would involve going this way. And if they do that, they escape the liquid phase. And when they are floating around above the surface, we call them a vapor. Now, I might slide a U in here because I'm Canadian, so if you see me spell vapor with a U in it, that's what's going on there. But what a vapor is the phase of a substance acting, oops, I messed that up, hold on. Acting as a gas, but below its boiling point. So vapors are allowed to exist at any temperature you want. But if the temperature is below the boiling point, then we have to call it a vapor, even though it's behaving like a gas. The gas is what it is existing as, but the term that we use to describe it is vapor. If this was water, for example, and it was water at room temperature, we have water vapor above our water at room temperature. We don't have water gas. Like, technically we do have a gas, but we don't call it that. If it was at 100 degrees Celsius, then we would call it, it would be water as a gas, which is actually steam. Now, if I have my container open like this, then what's eventually going to happen is that these molecules are going to evaporate, and then they'll leave. And they will probably never come back, because once they get out into here, it's a big world back there, and the glass that they left from is very, very small relative to it. The odds of those molecules finding our glass of water again are essentially zero. So, more of these will start to evaporate, and eventually this level will go down, and the water inside the container will eventually evaporate away. So this is why if you leave like a bucket of water outside after, and like maybe it collected water after it rained or something, and you just leave it there, then like 2-3 weeks later, the water will all be gone. It will have all evaporated away because it all slowly became a vapor. Now, if I did something different to my container, such as, say, putting a lid on it, then this escape action doesn't happen. And what ends up happening is that these molecules bounce around inside and eventually return to the liquid phase. And so evaporation is still occurring, but it's occurring at a rate that eventually will equal the rate of condensation where the molecules return. And so the liquid level will not change in this case, at least not noticeably. Now, this concept is going to be important in just a second, so we're going to come back to it. And there's just what I said, basically. So, all right. Oh, and we're going to talk about that right now. Okay. So, on the screen, I actually have a picture of what I drew. So, we'll draw on this one. What you'll notice here is that in my container, I have vapor molecules that are bouncing around, and they are filling this space. So shower steam is actually water vapor, yes. So steam is specifically defined as water, as a gas above 100 degrees Celsius. That's the strict definition of steam. But the colloquial usage that we use for steam is, oh, it's warm water vapor. So if you go into a steamy room, people will understand what you say, but a scientist will tisk-tisk at you. But you would not actually want to go into a steam room. Like, if there was actual steam, it would be above the temperature of boiling, and you would get scalding burns and then probably die very quickly. Inside our container here, we have, this is ethanol in this example here. We have vapor, and the vapor is going to fill all this space that is in pink here. What it's doing is it is pushing on this gray substance. This right here is liquid mercury. And what it's doing is it is pushing the column upward to do what is known as, or to manipulate what is known as a barometer. So a barometer measures changes in, like, say, air pressure and stuff like that. What this is doing is showing that if I had no vapor in the container and the level of the barometer was equal, when I allow the molecules to evaporate, which they do quickly, they exert this much of a force onto the mercury. And so this is known as vapor pressure. In other words, because our vapor is behaving like a gas, it must have the properties of a gas that we talked about on Tuesday. So that means it has a pressure, it has a volume, it has a temperature, and it has a number. Specifically, we're going to care about vapor pressure, because vapor pressure is an important rubric for determining the boiling point of something. Now, we're going to talk about the interactions between molecules at the bottom of the screen in just a second. That's actually the second half of today's lecture. But what I want to do is I want to go back to this right here. We'll leave the diagram in here. But I want to draw this again. Alright, so here's my liquid. Here are my molecules in the surface of the liquid. We'll suppose that this many are present at this temperature. So the next thing I'm going to do is I'm actually going to heat this up. So I'm going to put it on an oven coil, and I'm going to heat this up. And as all the molecules inside heat up, they will start to move faster. And if they move faster, then what that means is they have more energy and can thus escape more easily. If the molecules escape more easily, then there are more of them up here. And the pressure that they would exert increases as their temperature increases. So vapor pressure is linked directly to temperature. And the reason for that, again, is because increasing the temperature makes my molecules move faster, they can escape more easily, there will be more populating the vapor phase, and thus the vapor pressure increases. If I were to cool the solution down, then the molecules would move more slowly and less of them could escape. And if less of them could escape, there would be less in the vapor phase and the vapor pressure would go down. Now, the relationship is not linear. So if I plot temperature and vapor pressure on a graph, what it does is something kind of like this. It follows an exponential pattern. So as I heat stuff up, the vapor pressure increases. Now, eventually, it will hit an interesting number. And that interesting number is this, atmospheric pressure. Because what up here is pushing down on the liquid? It's the atmosphere. And my vapor pressure is going to push back at that. Now, at a low temperature, the vapor pressure pushes against the atmosphere, and it can make its way through, but that's really all it can do. It cannot push the atmosphere away entirely. But if I heat my temperature up enough to get to a certain point where the vapor pressure equals the atmospheric pressure, then what ends up happening is that the liquid is no longer being restrained by the atmosphere. And at that point, the liquid begins to boil. So if the vapor pressure of our liquid increases enough to equal atmospheric pressure, the liquid boils. And the temperature at which it does that is called the boiling point. So the takeaway here is that liquids boil when the vapor pressure equals atmospheric pressure. And so that's why we differentiated between boiling earlier and evaporation. Because evaporation happens all the time. It can happen at any temperature you want. But boiling is very specific. It only occurs at a specific temperature when the vapor pressure equals the atmospheric pressure. So that's the formal science definition of boiling. Now, the next thing that we want to talk about, and we're only going to kind of allude to this for now, when we get to intermolecular forces, we'll discuss this in all the detail, is what keeps these molecules from boiling on their own? Why do they stay in the liquid phase? And the answer is that I'm drawing these little dotted lines in here that are impossible to see because this is too tiny. These molecules don't repel each other. If they repelled, they would just immediately become a gas. Instead, they're actually attracted to each other slightly. But we talked about that in Chapter 5. We said that molecules are independent and they don't interact with each other. Well, that wasn't the entire story. That was kind of a, shall we say, a lie. Even though the molecules are independent, they're not bound to each other. They don't have bonds. But there is an attraction between molecules that we're going to discuss in the next section. And that attraction governs how easy it is for our molecules to escape the solution. If there's very little attraction, the molecules can escape easily, and then the stuff will evaporate very readily. This would be something like gasoline, where if you spill gasoline on the ground and you watch it evaporates before your eyes. It goes really fast. But if you spill water on the ground and you don't clean it up, water evaporates incredibly slowly. We'll talk about these intermolecular forces, which is the actual name of them, later on today. And so, in any case, that's what this is talking about down here. The slide is alluding to interactions between molecules and the result on vapor pressure. If my molecules interact strongly, they don't want to evaporate. The vapor pressure ends up being lower. So we'll talk about that again later. We've already talked about boiling, but here's the definition of boiling. Again, the boiling point is when the temperature is reached that the vapor pressure and the atmospheric pressure are the same. Now, this is actually very practical to us. There's really only one liquid that we interact with multiple times a week, I'll say, that we care about it boiling, and that is water. We boil water to cook stuff because water boils at 100 degrees Celsius. That's 212 Fahrenheit. That's hot enough to kill things like bacteria. That's hot enough to congeal proteins so that we can eat them, so you can have hard-boiled eggs. That's generally a hot enough temperature to do a bunch of stuff, and water is convenient. But let's suppose you live in Denver. In Denver, the atmospheric pressure is not 1 atm because you are not at sea level. So let's draw our little world map here. So here's the world. Here's the water and the ground beneath it. And here's our atmosphere. If you're at sea level, then the pressure that the atmosphere pushes down on you is 1 atmosphere. And so you have to heat water until its vapor pressure equals this amount. But if you live in Denver, which is the mile-high city, which I guess is up here, and you're trying to boil water, the atmospheric pressure is lower than 1 atm. This is obviously exaggerated because the atmosphere goes up for miles and miles and miles. I don't actually know the atmospheric pressure in Denver. I want to say it's like 0.97 or something like that. But it is lower. And so what that means is because this number is lower, and the vapor pressure has to equal atmospheric pressure in order for water to boil, water will boil at a lower temperature at high elevation. If you've ever bought something that requires you to boil water, the directions may have included something that along the lines of high altitude cooking instructions. And those instructions are, generally speaking, cook it for longer. Cook it at 15 minutes instead of 11 or whatever. And the reason for that is because the temperature doesn't go as high, so you need to cook for longer. The opposite happens if you were to cook, say, I don't know, let's say we're on the other side of the ocean here, or a lake, and we cook in this pit. So let's suppose that we're in Death Valley. If your elevation is below sea level, then the atmospheric pressure is higher than 1 atm, and water still boils when it equals atmospheric pressure. And so it'll boil at a higher temperature if you're at a low elevation below sea level. Now, obviously, if you want to cook at a higher temperature to cook stuff faster, you're not going to go to Death Valley or the Dead Sea. Like, that's ridiculous. What you can do is you could buy something called a pressure cooker. A pressure cooker increases the pressure in the headspace above the water. And it increases it so much that the water will stay liquid up to a higher temperature. It will not boil. And the reason that you might not want it to boil is because you might want it to have a certain volume that you put, like, I don't know, vegetables or something in to tenderize. And you cook it in the pressure cooker, and you could cook it more quickly because it's at a higher temperature. Maybe you want to do, like, sous vide or something, I don't know. When you open the pressure cooker, inside you have this situation. So we'll draw my pressure cooker down here. So here's my water. I have lots of vapor in the headspace. So in here, we could say the vapor pressure is much, much greater than atmospheric pressure. Because this is at, like, I don't know, 110 degrees Celsius or whatever. Let's suppose that you then open the pressure cooker. What happens when you open the pressure cooker? If you've ever opened a pressure cooker, what do you not point it at? I don't know if there's anybody who in the class who has actually used a pressure cooker. I have, and it's I mean, it's effective. It's not safe. I wouldn't say that much, but yeah, you never point it at a person, right? Because what happens now is that the vapor pressure is much higher than atmospheric pressure, and out here we have atmospheric pressure, which tries to fill in this space, but it can't, and so what ends up happening is all the steam comes out, and the water immediately boils until it goes below the boiling point of water. And so you get a ton of steam very, very quickly, which hisses out of the pressure cooker. And if your head is over that, you will get steamed, and you will be well done. So don't do that. Be very careful with a pressure cooker because it is dangerous if you don't manipulate it correctly. If you operate it correctly, it's perfectly safe. It's just be very careful when opening it to get your food out, because that's kind of the point. All right. So boiling is related to atmospheric pressure, and you can manipulate that pressure however you want to get desirable effects. I actually want to show you this in action. I don't think I have a video of it, but I can get one. How many of you have seen water boil at room temperature? I just have to find it. Water boiling at room temperature. Alright. So let me get the experiment set up here. Alright, there we go. So that'll work. Window capture 2. That's the right window. Let's see if... There we go. Perfect. Okay. Alright, so what this is this is a container of water with a thermometer in it. It is currently 20.7 degrees. What he's going to do is he's going to seal this in a vacuum chamber and remove all of the air from around the outside of the container, which means that the atmospheric pressure pushing down on the water in the container will be reduced. And if we can reduce it low enough, it will then eventually equal the vapor pressure of water. And something should happen, and it will happen very quickly. So he's going to put the container on, hook the vacuum pump up to it. We'll just fast forward through this until he does. There it is. Alright. So he's going to turn on the vacuum pump, remove the air from it, and you should see something happen relatively quickly. I'm just going to peek ahead to see when it happens. Okay, it will start soon. Let me see if we have any audio here for this. There's really no audio. Okay. Alright, I don't want to go forward too much. There we go, okay. What do you see is happening inside? There it is. And now if you've ever watched something boil before at your stove, this is more or less what you see. You just see like small bubbles at first, then you start to see more bubbles, and then you get to this point, which is called a rolling boil, where everything is just boiling. Now, if we go up to the thermometer, it's certainly not 100 degrees Celsius, right? We didn't heat this up, so let's get the temperature. And there's glare in the way, unfortunately, so he's got to move the camera here. But you can see that the temperature actually went down. Why did the water get colder when it was boiling? I'll give you a hint. We talked about this at the very start of today's lecture. Why did the water get colder when it was boiling? Type it in the chat if you have any idea. Not quite from the pressure change. I mean, the pressure change eventually caused it, but that's not the answer I was looking for, unfortunately. So evaporation is what's happening, but why would the temperature go down when stuff is evaporating? I'm looking for a very specific word, and it does begin with E. If you have your slides handy, go back to the first slide in this section that we started with today, with that little triangle diagram. And I wrote all over it, and I wrote some words that began with E. Oh, it's the other one! Exo means the energy goes out, and out would be out of the water and into the thermometer, which should get hotter. Endothermic, there you go. So if something is endothermic, the energy is going into the water. And the energy would be heat or ambient temperature from outside sources, which would be the thermometer in this case. So as the water boils, the thermometer loses that heat because it's giving that heat to the water to boil it. And as such, the thermometer's temperature goes down. And it goes down pretty quickly, actually. So the real reason why this is happening and why the temperature is going down is because boiling is an endothermic process. We have to put energy into water to make it boil. Removing the atmosphere gives it the ability to do so, but it still needs energy. And there's energy all around us in the form of temperature. Because molecules will bonk into each other. And this will actually keep going down for quite a ways until all the water evaporates away. So that's boiling at room temperature, and apparently that's the viewer count because I closed the wrong thing. Look how many people are watching. I just have that on screen to make sure that I'm not lecturing alone. Because if I ask questions to a room and nobody's there to answer, I might sit there for 20 minutes and be like, man, they must be really stuck. So I have that handy. All right, so here's some practice questions for you to think about. And we'll go over the answers to these in just a second. But let's suppose that I have liquids A and B, X, Y, and Z. Liquid A has a vapor pressure of this much at room temperature. You'll notice I'm giving you numbers in torr, so you're going to have to go look up what the conversion for torr to ATM is. Will liquid A boil at room temperature? Will liquid B boil at room temperature? And then arrange liquids X, Y, and Z in order of their boiling point. Now, remember, if a liquid has a high vapor pressure, that's because it does... Well, so if a liquid has a high vapor pressure, you don't have to heat it up very much to get to 1 ATM. If a liquid has a low vapor pressure, you got to heat it up a lot more. Okay? Now, not all of those are in the same units, so you do got to do a little bit of math. You got to get your calculator out and turn them all into the same units. I would recommend ATM. Okay? Go ahead and do that, and we'll go over the answers in just a second. Alright, I'm back. Let's see here. So we have some answers. Let me see if I can guide you in the right direction here. So remember that... Oh, I'm on the wrong pen. That's why. Remember that liquids will boil if their vapor pressure equals atmospheric pressure. We're going to assume that all of these are at sea level. And so what you have to do is you have to take this number and tell me if that number for its vapor pressure is above atmospheric pressure, below, or equal to. And if it's equal to or higher than atmospheric pressure, it will boil. And then you have to do the same thing for this one. And then down here, turn these all into the same unit, and then you can arrange them by boiling point. Remember, if the vapor pressure is high, the boiling point will be low, because you don't have to get it much higher to get it to 760. If the vapor pressure is low, then you have to heat it up a lot more to get to a boiling point. So try that. I'll come back in another 2 minutes, and we'll go over the answer. All right. Let's go over the answers. So for the first part here, I want to know if my liquids will boil based on their vapor pressure. So for liquid A, its vapor pressure is equal to 760 torr. And if we go look up in the notes earlier in Chapter 7, then we would see that 1 atmosphere is actually exactly 760 torr. So in other words, this is just 1 atmosphere. And if its vapor pressure is equal to 1 atmosphere, that is equal to atmospheric pressure. And so liquid A will boil. And RT is room temperature. Well, let's look at liquid B. I could turn this into ATM, and that will be 0.284 ATM. That's less than 1 ATM. So no, it will not boil. That's how we figure out the first two. Because you got to be above atmospheric pressure in order to boil. Now, if I heat it, it might boil at a higher temperature. What that is, we're not going to solve in the problem because we don't have enough information. All right. For this next one, we got to get all three of these into the same unit. So what I'm going to do is I'm going to turn X right here. Where's my cursor? There it is. We're going to turn this into atmospheres. So 335 torr. We can turn torr into atmospheres just like we did before. There are 760 torr in an atmosphere. So this is going to equal 0.441 ATM. And that's going to be the pressure of X. Pressure Y is already in ATM, so I could just leave it there. And then pressure Z here, we could do the same thing. And you might do this calculation and go, wait a second, I got a number that was higher than 1 ATM. We'll put PZ down here. And you can do that. What would that imply the boiling point must be, though? If these are vapor pressures at room temperature, what would the boiling point of Z be? Would it be at room temperature, above, or something else? I guess the better way to pose this question is to say, which of these has a boiling point below room temperature? One of them does. Can things have a boiling point below room temperature? Sure they can. What temperature does the air that you are breathing boil at? Well, the air around you is a gas, right? So, it must have already boiled, because the current temperature is too hot for it to be a liquid. So if these are our vapor pressures for these liquids at room temperature, this one is already above 1 ATM, and thus it will boil at this temperature, and it will actually boil at a lower temperature than room temperature. So X is currently at room temperature, because they all are at room temperature. But it would boil at a lower temperature than room temperature, because it would still have 1 ATM of pressure, even if you cooled it down slightly. The other two must be liquids at room temperature, because they have not gotten to 1 ATM. So we would conclude that this has the lowest boiling point, because it's going to boil at a cold temperature relative to room temperature. But now we got to pick which one's the next highest and which one is the highest. And again, remember, if vapor pressure is high, boiling point is low. And if vapor pressure is low, boiling point is high. Which one has the lowest vapor pressure? I guess we could write that down. So vapor pressure is low, boiling point is high. This is probably the words you were looking for. Which I'd said, but I didn't put it in such short and concise language. So who's going to have the highest boiling point? Is it X or Y? And it is X. Very good. So this is the highest boiling point. And this one is in the middle. And the reason for that is because boiling point is you got to get to 1 atm, right? It's got equal atmospheric pressure. And so this one, you don't have to heat it at all. It's already done. This one you have to heat a little bit. And this one you have to heat a lot before it's done. All right, that's our chapter on boiling. Any questions, let me know. I think the next slide is, yeah, it's just this. So I will put the title card up. We're going to take a break. We're due for a break anyway. Boop. Do I have the timer up? No, I need it up. That's not the timer. That's just a please update me. All right, so I'm going to do this. We'll put the music back on, and I'll see you in a little bit. Hello again. Alright, so let's get back to our lecture. Hope everybody was able to take a short break. So, in our discussion of boiling here, what we have learned is that if vapor pressure increases, the liquid will eventually boil once it reaches 100 degrees Celsius. Or not 100, I'm sorry. Once it reaches 1 atm. For water, that is 100 degrees Celsius. But for different liquids, they boil at different boiling points. They still get to a vapor pressure of 1 atm. But what differentiates between various particles and describes how they behave? And it turns out the answer to that is in this section, which is probably the most important from this class for biology. So this is a really important section that we're going to spend the rest of the period on today talking about. All right. So the first thing we want to do is we want to describe how molecules interact with each other, because they aren't independent like we have believed so far. The interactions between molecules are called intermolecular forces, and intermolecular forces are very weak. So this right here is my intermolecular force. Now, don't worry what these numbers mean. This unit is totally worthless to you, because we're not going to do anything with kilojoules per mole in this class. But what's important is that the number represents how strongly these things are held together. For instance, the HCl atoms in the HCl molecule are bonded together and have a bond strength of 431. But the HCl molecules themselves stick to other molecules with a strength of only 16. They are very, very weak in comparison, and if we heat these slightly, these are the first things to break. When energy is added, bonds will break if you add lots of energy, but intermolecular forces will break if you only add a little energy. The stronger these intermolecular forces are, the less likely the molecules are to wander off on their own. For instance, in molecules where the intermolecular forces are very strong, the molecules will stay locked together in a rigid shape, and you get a solid. If the forces are moderate, then you get a liquid, and the molecules will move around, but they're still sort of connected to each other. Like they at least remain in close proximity because they're attracted to each other, even though they're moving. If there is very little attraction between the molecules, then the molecules fall apart from each other, and you get independent molecules everywhere, and you get what is a gas. Now, again, it does not take much energy to remove these forces, which is why over the course of just raising the temperature from like room temperature to 100 degrees Celsius, that's all that you need. To break water apart completely into hydrogen atoms and oxygen atoms, you need to raise its temperature to above like 3,000 degrees, which is actually very, 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 very high. All right. Now, if my molecules stick really well, they aren't going to want to boil, because remember that if I... Let me hide this really quickly, and we'll just draw on the slide. Remember that if I want my liquid to boil, my molecules can't all be stuck together, because if they're all stuck, they can't get out of here. So, with that in mind, here are two liquids that have two different boiling points. So, one is water, and it boils at 100 degrees Celsius. But HCl boils at negative 85 degrees Celsius. So what do you think sticks together better? HCl molecules with each other or H2O molecules with each other? Which will stick together and resist boiling? HCl or water? Which will stick together more tightly? Which has the stronger intermolecular forces? And water is right. And the way that we can tell that is, oh, water has a higher boiling point. Its intermolecular forces must be stronger because we have to heat it more to bust them apart. HCl, we don't have to heat at all. It boils at negative 85. Therefore, its intermolecular forces must be very weak. And we don't have to put in any heat to break those apart. Those molecules will separate virtually on their own. Now, why is this? What we need to do now is we need to describe the different intermolecular forces in molecules so that we understand what it is that is holding these things together. And the first thing that I'm going to do is talk about dipoles. So I'm going to leave this picture on the screen, but I am going to go back to this. We'll just put this up here. You might remember from Chapter 5, where we drew molecules and we determined whether they were polar or nonpolar. Remember that? Yeah, Chapter 5 never goes away. It's always here. So we drew water like this, and we said, okay, I can draw polarity arrows pointing at the more electronegative element along the bond. And then when I sum those together, I get the polarity of the molecule. Do you remember this? So now what I'm going to do is I'm going to represent this molecule as just a little blob here. And if it's polar in this orientation, I'm going to put the positive or the negative end on this side and the positive end on this side. So I now have a molecule that is polar. If I were to take this molecule and introduce it to another molecule, and I gave it choices, which molecule would it interact with? This first one is just this. That's all it's got. It doesn't have any dipole on it. It's nonpolar. But this one does have a dipole. Which would water want to interact with? The one that has a dipole or the one that does not have a dipole? And then answer the question, why does water prefer that one? Which would water prefer? It does prefer the dipole one, but why? It's not because of the boiling point. I'll give you a hint. It is something on the screen. That's the reason why. It's because the positive and the negative part are attracted to each other. Whereas there's no attraction here. It's just, they're two things that would bonk into each other and be like, huh? But the water will interact with another polar molecule because the positive part of it will line up next to the negative part of it. So if I had two water molecules next to each other, they would actually interact with each other in the same way. So this is the negative part. And this is the positive part. And these two would hang out. And so water sticks to other water molecules for that reason. This interaction is what's called a dipole-dipole interaction. Dipole-dipole interactions occur between two molecules that have dipoles. And you can see in the picture above on the slide that all the molecules on the left that are blue are sort of turning and pointing in various ways, but they're trying to do so such that the opposite charges line up and the like charges are as far away from each other as they can be. And so I'll zoom that in for you to see. On the right side, we have the same thing going on, but this would be more akin to a solid because all the molecules are lined up in an orderly fashion. Now, if I make my molecules more polar, which means that the difference in electronegativity along this molecule is larger, the bond becomes more polar, and the consequence of that is that dipole interactions become stronger. And if the interactions become stronger, what will happen to the boiling point? So if this happens, then my molecules hold together even more tightly, and the boiling point will go up. Very good. So, depending on how polar our molecules are, they will hold together with each other more strongly. And if they hold together more strongly, the boiling point goes up. So, the more polar it is, the higher the boiling point will be. Now, as you make a molecule bigger, polarity tends to go down. So what we're going to do here is I'm going to make a... Let me do it this way. Oh, it's going to make me reconfigure this. Hold on. So, image, canvas size, 2000. Oh, it didn't do it right. All right, so what we're going to do is we're going to make a little chart here. And our chart's going to plot... That was bad. On the bottom, we're going to plot the mass of the molecule. And I'm going to plot that in grams per mole. Because as molecules get bigger, they become less polar. They're more bulky. And then over here, and I got to draw this sideways on a screen. I went off the screen, didn't I? Let's just move this guy over there. Alright, so this first one that we looked at was dipole. And it didn't save my color. There we go. And these are very strong, but as molecules get bigger, they tend to become less so. We're going to come back to that and describe other intermolecular forces in a second. All right. And again, down here at the bottom, smaller molecules have stronger dipole forces because the polarity of a molecule is linked to its mass. Molecules become less polar when they become heavier. Now, what I'm showing you on the screen is actually a dipole-dipole interaction, but this is a special type which has a really obnoxious name, and it's called a hydrogen bond, even though it's not a bond. It is an intermolecular force. And for the hydrogen bond to occur, what we have is something that is delta plus right next to something that is delta minus, and we have a very small amount of space between it. I don't want you to think this dot is an electron, so let me get rid of it. So the conditions to make a hydrogen bond, and a hydrogen bond, again, is just a dipole that is stronger. To make a hydrogen bond, you need hydrogen, duh. That hydrogen needs to be bonded to a very electronegative atom, and so that gives us only 3 choices. And I'm going to write actually bonded, because I don't want you to get mistaken for hydrogen bonded. And so, is my H bonded to NO or F? Yes, it is. There's a bond right here. I'm going to erase my stuff here so that we can show this again. Then the second qualification is, can I point the H at an electron non-bonding pair on some other NO or F? So let's check our conditions. Does H have a bond to a highly electronegative atom? It does. It's this right here. Then condition 2. Can I point H at the electron pair on some other nitrogen, oxygen, or fluorine? Yes, I have it right here. If you can do that, what you have is a hydrogen bond. And if you are eligible to make a hydrogen bond, then the dipole force that you have created is much, much stronger. So if I go to my little diagram here, and we add in hydrogen bond, it's just like a dipole, but it's stronger, and it does the same thing here too. On the slide, I have 4 different molecules, and each of these has a hydrogen bond in the circled area. Let me get rid of my text on the screen here. There you go. So each of the circled regions indicates a location where hydrogen is fulfilling the hydrogen bond. And every time we fulfill the 2 conditions. 1, is it bonded to an NO or F? 2, have I pointed it at the electron pair on an NO or an F? And you can see that that's happening over here. The whole thing that I've circled is the hydrogen bond, because you need both of those electronegative atoms and the H sandwiched between them. This is the strongest type of dipole interaction that we're going to talk about in this class. And it is so strong that it makes water have a boiling point far, far higher than it should. And I'm going to show you a slide of that in a little bit. First, what I want you to do is just to practice your Lewis structures, because it's been 2 chapters since we've done this. I want you to draw the Lewis structure of these molecules. So, for instance, I would draw CH4. And then I want you to draw a second copy of it. And then ask yourself, can I make the copies hydrogen bond with each other in some way? Can you fulfill the 2 conditions? For this one, I don't have any N's, O's, or F's, so it doesn't work. I'm not going to be able to hydrogen bond CH4. But go on to this molecule, draw its Lewis structure, draw a second copy of it. Can you find a way to make them hydrogen bond with each other? If you can, hydrogen bonding occurs. Do the same thing with this one and this one. Okay? I'll give you a few minutes to try that. We'll go over the answers after that. How are we doing? Need more time to draw the structures? Or do we have the answers? Alright, let's go over the answers. I hit the wrong button. Alright, so let's draw the Lewis structures of these. So H2N and H2. Hopefully for this one you got a molecule that looks like this. And then I'm going to make a second copy of it. And now what I need to do is I need to fulfill both the conditions. The first condition was, do I have a hydrogen bonded to an electronegative atom, N, O, or F? And the answer to that is, yeah, I have tons of them. In fact, all of these bonds would qualify. Now the second is, can I point the H at the electron pair on another N, O, or F? And the answer is, well, I have an electron pair right here. So if I just point this guy over here, it'll work. Now, that does require me to redraw the molecule, but I could do something like, say, this. That's not what I wanted to do. And we'll just kind of shimmy it over here, and then, boop, there it is. So now I have a hydrogen bond, and it's just this right here. If I had done that, it would be that right there. Ooh, I don't know why you're doing that. Now, hydrogen bonds don't have to go in straight lines, but the best ones do. So ideally, it should be in a straight line, and this would straighten out to make it be linear. But I can't really do that without drawing the whole thing over again. So this one definitely does hydrogen bond. Let's look at CH3F. Let's look at it, and then I'll draw it immediately under the problem guide. All right. Do I have a hydrogen bonded to an electronegative atom, N, O, or F? And it turns out in this case, I don't. There's no H's bonded to this F. They're all bonded to this C, but there's nothing here. So I cannot hydrogen bond CH3F because it fails condition 1. H2S does the same thing because the H's are not bonded to an NO or an F. They're bonded to an S. And that's not electronegative enough, so it can't do that. So the only one that can engage in hydrogen bonding is the diethylamine. Or that's not what that is. I don't know what that is. H2N and H2, we'll call it. It has some common name out there. Diamine, maybe that's what it's called. All right. Now, the next question that you could do is you could draw ammonia with water. I'll do that really quickly because I do want to move on to the next section. I want to finish chapter 7 today. HF and HCl will not hydrogen bond with each other because Cl is not going to be able to do that with this H. But ammonia and water totally will. And so we could show that by drawing. Just clear these. So here's ammonia. And here's water. And I got to select an eligible hydrogen to be bonded to an NO or an F, and actually all of them are, so I'm going to pick this one. I'm just going to point it at this electron pair right here. And so if I were to say do this, let me see if I can do this. I don't know if this is actually going to... Ooh, look at technology. Ooh, there we go. There we go. There's my hydrogen. Oops, I didn't draw it as a dotted line. There's my hydrogen bond right there. Now, you could have done this the other way. You could have used the water to give its hydrogen to the nitrogen, and then I would have connected up... Oops, that's not what I meant to do. I would have instead put the water up here somewhere. In that instance, the roles of the molecules would change. And the way that we label these, and this might come up in a different class, so just in case you need to know this. The molecule that is donating the H is the H bond donor, and the molecule that is donating the electron pair is the H bond acceptor. Some molecules are H bond donors, but are not H bond acceptors, and vice versa. Some molecules can do both. It all depends on the structure. All right. This page right here shows how hydrogen bonding has greatly increased the boiling point of water. So you'll notice that if I was to follow this line like this, I would get a pretty linear trend. If I was to follow this blue line, I get a pretty linear trend too. Down here, these molecules don't hydrogen bond. They're nonpolar, it turns out. And we're going to see why nonpolar things have a higher boiling point as they increase in just a second. This molecule doesn't hydrogen bond. This one doesn't. This one doesn't. But this one does. And it's because of hydrogen bonding that the boiling point increases from negative 100, which would be a really cold shower in the morning, to positive 100, and is stable enough at room temperature that life can actually proliferate. So it's because of hydrogen bonding that this is even possible. So thanks, hydrogen bonding. It's also due to hydrogen bonding that proteins and such things as viruses can also exist. So, we take what we can get. All right. In this structure right here, this is what ice looks like when you zoom it in. Ice is the conglomeration of water molecules that are all aligned in a very specific pattern. And that specific pattern has oriented itself such that hydrogen bonds can form as often as possible. So for this molecule right here, here's a hydrogen bond. There's one. There's another one in here. There's one here. And then there's one somewhere in here too. So all the molecules arrange themselves in these little hexagonal circles. And by doing that, the structure of the water becomes a solid because all the water molecules lock into place. Now, they don't do that for long because even though these hydrogen bonds are strong, they're not as strong as actual bonds. And so water becomes a liquid after 0 degrees Celsius, which is still considerably high for most liquids. All right. The last intermolecular force that we're going to talk about today is called the London Dispersion Force. And London dispersion forces are basically a last option for molecules that have no other alternative. For example, if I drew CH4, CH4 is nonpolar. It has no dipole to speak of. What can it do? It just has electrons. Well, anything that has electrons, the electrons will move around randomly. And in this side, my electrons are pretty evenly distributed. But on this side, they're not really distributed. They're just kind of over on the same side by chance. If this is true, then what I can do is I can say, oh, okay, most of my electrons are on this side. That makes this delta minus. If most of my electrons are on this side, these guys are going to repel away from that and create a delta plus. And if I had another molecule over here, it would see this and go, oh, my electrons want to be over here, so that we can be delta minus also. But the second one of these randomly just goes back, this is canceled, and when that is canceled, this is canceled, and then so on and so forth. So these are very temporary, and they're due entirely to the fact that the electrons move around randomly. The more electrons I have, the more randomly these intermolecular forces can occur, and then, and only then, they can act like baby dipoles. Alright. Now, I hate this picture, I'm going to skip it, but the interaction that occurs between the temporary dipoles is the London dispersion force. When you have electrons in a molecule, and those electrons move about randomly, at some period, they will have an uneven distribution. They will not be exactly distributed over the molecule. When that happens, you create a London dispersion force. Now, this is a little bit misleading. I wrote nonpolar molecules here, but really the only requirement is that you have electrons. In fact, all molecules have electrons, so all molecules have dispersion forces. It's just that if you are nonpolar, this is your only option. Hydrogen bonding requires a very polar bond. Dipole requires a dipole. Nonpolar molecules, they only have dispersion. This is all they get. How do you increase the dispersion force? You do this by increasing a molecule's polarizability. And what polarizability refers to are these two things. The first is just simply how many electrons are available to move around. The more electrons you have, the more likely you are to have an uneven distribution. For example, if you flipped two coins, what are the odds of them both coming up the same heads or tails? Or actually, no, I'm sorry, I did that wrong. What are the odds of them coming up one as heads and one as tails? And the answer is 50-50, right? But if I had 50 coins, what are the odds of 25 of them becoming heads and 25 of them becoming tails? It's not 50-50 anymore, because now there are a lot of opportunities where it might be 24 and 26, or 27 and 23. And in all of those cases, there would be an unequal distribution of heads versus tails. With our electrons here around an atom, the more electrons that are there, the more likely one of them is going to be on the wrong side. And when that happens, a London dispersion force is created. Now, when those interactions are created, the shape of the molecule matters too. If molecules can't interact with each other because they're too round and can only touch at like one location on a sphere, then the interaction between those molecules is weak, and we're going to see that in a second. Now, how do we know how many electrons something has? Well, if you have more electrons, the dispersion force goes up. And we can relate more electrons to a very simple thing. If you have more mass, you have more electrons, because the higher the molar mass is, the more electrons there are. Xenon has more electrons than neon, and xenon has a higher mass than neon. So when we go over to our little diagram here, oops, that's the wrong window. So where's our diagram? There it is. When we go to this diagram, we'll just hide this behind the chat, and we put in dispersion here, dispersion is really crappy until it gets really big. So dispersion has the potential to become the best force of all if the molecules are really large in terms of their mass. The other forces that we've talked about today, the dipole forces, are only strong if the molecules are tiny, because tiny molecules have the strongest polarity. Filling up a molecule with mass is generally just you filling it up with carbons and hydrogens, and those are nonpolar, and so the overall polarity goes down. So that's dispersion. Dispersion is just a temporary force that occurs randomly, and the more electrons you have, the more likely it is to randomly occur. Now, what happens if you have two molecules that have the same formula but different shape? This is what happens. Here I have C5H12, which has a Lewis structure like this, C, 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 and then off of each of these branches is an H, but I'm going to save some time and not draw those. And you can see it's roughly a sphere. And my spherical molecules can interact right here. But C5H12 in the linear form looks like kind of a hot dog, I guess we'll say. And these molecules can get all cozy next to each other like that. It's kind of like if you were cuddling with your significant other. If you cuddle with them, do you put your feet against their feet and say cuddling? Or do you put your belly or back against their belly or back and say cuddling? You get more contact area if you lie horizontally with each other as opposed to on top of each other, like vertically. And that's the whole point of cuddling, is you want contact, right? With molecules, it's the same. How do my molecules cuddle? Well, they try and contact each other as much as they can so that the dispersion forces that they are going to make have more ability to contact and thus stick together. And you can see down here that the boiling point of these molecules, these are in Kelvin, but for the N-pentane, which is the linear version of it, is about 20 or so, I'm trying to do math in my head, 27 degrees Kelvin, which is 27 Celsius, higher than the neopentane. All right. And this is all just stuff that we said. So all molecules have dispersion. Dispersion is usually the weakest. But if the molar mass of the molecule is very, very high, dispersion becomes significant, and it can be the highest of all. In molecules known as lipids, which are important for making cell walls, those molecules have tremendously high molar masses. They're also just carbons and hydrogens chained together. Because they are so big, their molar mass is very large, they have a lot of electrons and they have a lot of dispersion force. Eventually, as the length of those molecules increases and their mass increases, they tend to become attracted to other molecules of the same type. And so things like lipids can be stacked all next to each other and form a barrier, which you're actually going to see in next week's lab when we talk about solubility, because it involves stuff like oil. Cooking oil is like this too. It's made of molecules that have only dispersion forces, but because there's so many dispersion forces, it becomes a liquid at room temperature, as opposed to a gas. All right. For these two molecules, let's just draw them out really quickly, because I'm going to run out of time here. One of them is more polar than the other one, and one of them has stronger dispersion than the other. Which is which? Which one has the strongest dispersion? Type it in the chat. Which of these molecules has the stronger dispersion forces? Oh, I lost some electrons there. Sorry, my pen didn't work. I'm bonking the mic with my beard or something. I'm just looking at the bar go up here. Let me move it real fast. Any idea which one has more dispersion? What do we need for more dispersion? Molecule with more dispersion forces has a higher what? There you go, a higher mass. So which molecule has the higher mass? Is it CH3F or CH3I? It's CH3I. Very good. So this is the higher dispersion. All right. Which one is more polar? And thus has stronger dipole-dipole forces? They don't have the same polarity. What governs polarity? And it is CH3F, but how do we know? Where'd my pen go? There it is. How do I determine polarity? Well, if I know that this is the case for this, how do I know that that's where the arrow points? I have to go look up the electronegativity of it. And that's in Chapter 5. If you look up the electronegativity of I versus F, F is higher up on the periodic table than I is. And therefore, F will be more electronegative and thus will be more polar when connected to C. Oops. All right. Now, we can't ask the question which of these two has the higher boiling point. And the reason for that is because if I go to this chart that we had from before, I don't know where on the chart I am. So if the molecules are considered to be low weight, I would be over here, and I would say, oh, CH3F is definitely higher. But maybe it's above the weight threshold, and then, oh, CH3I would be higher. And that is hard to tell, so you're not going to get questions like that. I'm going to give you questions that are comparable to each other. Or I might just say, like, hey, these molecules are small. Which force is the strongest? Hey, these molecules are very big. Which force is the strongest? Alright, so to summarize intermolecular forces, there are many factors that we have to consider. For tiny molecules, we care about dipole and H bonds the most. They are the strongest. H bonds are the strongest of all. And then dipole is the second strongest for small molecules. For large molecules, everything reverses, and dispersion are the biggest. Oops. And again, you can look at that chart that we constructed on this to see that. All right, so the last thing we're going to do today is these practice problems here. One of these molecules is a solid at room temperature, the other is a liquid, and the third one is a gas. Which is which, and tell me why. And then you can do the drawing ones at home. But what I want you to do is in the chat, type in which one is the solid, which one is the liquid, and which one's the gas, and then explain why. Tell me why. I'll give you a hint. If you look up the electronegativity of C and H, you'll find that the difference is below the threshold for polarity. So these are all nonpolar. Anything with only C's and H's are nonpolar. What does that tell you about the intermolecular force, and which one must be which? Type it in the chat when you've got it. I was hitting the wrong button on my keyboard. Is it a solid at room temperature? What reason would you give to choose that? I'm not saying it's wrong. I'm not saying it's right. I just want you to explain your thought process, because then that might convince you. Because from what you typed, it makes it sound like you aren't sure. And I want you to be sure. Okay, that's a higher mass. So what does that mean? It is heavier. What does higher mass relate to the forces that we talked about today? Higher mass has more dispersion. Very good. So you have to sort these by their mass. And whichever one has the highest mass will have the highest dispersion. And if it has the highest dispersion, it's going to be the one that is held together the most. In other words, the solid. So this guy's the solid. This one must be the gas because it's the lightest. And the one in the middle is the liquid. I'm going to leave the pictures on the bottom part for you to draw on your own because we're out of time for today. But I believe that's the end of the chapter. It is. Hooray. Make sure you get the homework practice down here at the bottom. All right. I want to thank everybody for coming out tonight. On Tuesday, we will start Chapter 8. Chapter 8 and Chapter 9 are kind of short. It'll probably be more, hey, we can do this in a week sort of thing. At some point, we will get to Chapter 10. Chapter 10 is a little longer. But Chapter 10 is the last chapter, so we're very close to being done. You are now 70% of the way through Chem 121, so hang in there and stick it out because we are almost at the home stretch. Thanks for watching. Oops, we're not on a break now. We're done. In fact, I could just turn all of this off, right? Oops, not that one. I could just... Goodbye. Goodbye. There we go. Thanks for watching. I'll see you next time.